All right, today we experience looking at sequences. Again, we've talked about sequences before when we were talking about linear equations. Today we're going to experience sequences when we talk about um, exponential functions. And so we're going to look at both of those things today. So let's take a look at what we're going to do. Our objectives for today are threefold. Number one, we're going to determine if a sequence follows an arithmetic or geometric pattern. Number two, we're going to write a recursive rule based on the sequence that we see. And number three, we're going to write the sequence based on the rule that we see. So let's jump right in and get started. So the first objective is to determine the type of sequence that we see. So I just want you to take a look at A, B, C, and D and see if you can figure out what the pattern is in each of these specific instances. Okay, I hope you see on letter A that the pattern is we're repeatedly adding 7. On B, I hope that you see that the pattern is we're repeatedly multiplying by 2. On C, this one's a little tougher, but I hope that you see on this one what we're doing is we're dividing by 3. And then finally on D, I hope what you're seeing is that we're subtracting 12 each time. Now, two of these should look familiar. We've talked about the type of pattern that is a constant add or subtract. So A and D are both examples of what we call an arithmetic sequence. Because if you'll remember, an arithmetic sequence is a sequence that follows the pattern of adding or subtracting the same number over and over and over again. That's the type of pattern or sequence that we saw when we talked about linear equations and linear functions. B and C are patterns that follow multiplication or division. In fact, we're going to call them all multiplication because multiplying by 2 or dividing by 3, division can be written as a multiplication. So instead of saying division by 3, I'm going to say that's the same thing as multiplication of 1/3. By putting that 3 down in the denominator, that's like I'm dividing by 3. Okay, so these are what we call geometric sequences because geometric sequences are sequences that are formed by constant multiplication. Now, this should sound a little bit more familiar to what we're talking about here with exponential equations because remember, exponential equations happen by taking that base multiple times. And so by multiplying that base multiple times, that forms an exponential equation. So when we are asked to do objective number one, determine the type of sequence, what we are specifically looking for is the sequence formed by consistently adding or subtracting the same number over and over? If it is, it's called an arithmetic sequence. If the sequence is formed by consistently multiplying by the same number over and over and over, that's what we call a geometric sequence. All right, let's move on and look at our next objective. Okay, our next objective says I can write a recursive formula for each sequence. So these are the same 4 sequences that we saw on the last slide. So if actually there are 5 here, but the first 4 are the same 4. So this first one we said was found by adding 7. So a recursive formula, remember this is the one that we've seen before. This is the one that starts with the now equals and the next equals. So in this case, the now is where the sequence begins. So the sequence begins at 3. And the next is formed by adding 7 each time. So we're going to take the now and then add 7. So again, if you'll remember this one, I start at 3 and then I add 7 to that and I get 10. 10 is now my new now. So now plus 7, add 7 to 10 and I get 17. Then I go to 24, or I add 17 plus 7 and I get to 24. So that's where that recursive rule, because I'm repeating that process over and over. So looking at B, this one, again, we said the thing that we are doing over and over and over again is we're multiplying by 2. And so again, a recursive formula is going to have two parts. It's going to have the now and it's going to have the next. In this case, just like before, the now is where we begin. So we begin at 3. And then the next tells me how I get to the next digit in the sequence. So in this case, I would take 2 times the now. Remember, geometric sequences are formed by multiplication, constant multiplication, and so that's what shows as we do this problem. All right, so let's try C now. What would the now on C be? Good, it's 48. And now to get the next, remember we always want to use multiplication, so what are we multiplying each time? That's right, this is that tricky one. It really looks like I'm dividing by 3, dividing by 3, dividing by 3. But the way I can rewrite division by 3 is multiplication by 1/3. And so I'm going to take 1/3 times the now in order to get that next term. Okay, looking at D. This one we said was subtracting 12 each time. So if it's subtracting, that's an arithmetic sequence. And so I'm going to start just like before. The now is 100. But to get the next, I'm going to take the now minus 12. So again, arithmetic, plus and minus, geometric multiplication. Try E on your own. All right, when we look at E, it looks like this time I'm dividing by 2 each time, dividing by 2 and dividing by 2. So remember, we have to write that as a multiplication. So dividing by 2 would be the same as multiplying by 1/2. So if it's multiplying by 1/2, I'm going to start with the now is 20, and the next would be 1/2 times the now. So that's making sure we can write recursive formulas given a sequence. So 2 things to remember on recursive, they always have 2 parts. The now, where we begin, and then the next tells us what we are doing repeatedly. One more time, addition and subtraction are the arithmetic sequence. Multiplication is the geometric sequence. Now, it may be hard to understand why this fits into our problems right now. Why are we doing this when we're talking about exponentials? And it fits, you'll see here in our third objective how it kind of fits. But I want to remind you before we move to that third objective that an exponential function is always in the form of y equals a times b to the x. Remember, in this, the a is the starting point or the initial amount, and the b is that common multiplier. Now, some of you may already be beginning to see how this may fit together in writing an equation, but we're going to look because our next objective is asking us now to look at a rule that's written and come up with the sequence that's formed. So it's just opposite of what we did here on objective number 2. All right, so here we go. This one, the first one says a sub n is equal to 4n minus 1. Now, the format of this problem may seem a little bit strange, but I think that you'll see that it's something that we have dealt with before. Remember that little n tells me what term of the sequence that I'm talking about. So if I want to lay out my sequence here, I'm going to look for what is the first term. So that means I want to find A sub 1, the first term of the sequence. So if I've replaced n with a 1 on the left side, then I'm going to replace n with a 1 on the right side. And then I have a simple arithmetic expression to simplify. So 4 times 1 would be 4, and 4 minus 1 would give me an answer of 3, meaning 3 is the first term in my sequence. To look for the second term, I'm going to replace n with 2 because the second term is a 2. So in this case, I'm going to take 4 times 2 minus 1. So 4 times 2 is 8, and 8 minus 1 is 7. So the second term in my sequence is a 7. I can continue on with this problem by finding the third term and plugging in a 3. So 4 times 3 minus 1. 4 times 3 is 12. 12 minus 1 is 11. So my next term is 11. And then finally, the fourth term, I would replace n with 4. So 4 times 4 is 16. Minus 1 is 15. And I get that 15 is my next term. Now, we should hopefully remember this from last time. I see that what my common thing that I'm doing here is I'm adding 4 each time, adding 4, adding 4, and that should match over here to my slope of my linear equation because an arithmetic follows a slope intercept form of a line. It follows a linear pattern. All right, I knew that one was arithmetic because of this letter A. Now, sometimes they don't tell you that letter A there, but if you see that letter A, that's a hint to yourself that this should follow a linear pattern. We should be adding or subtracting the same number over and over again. All right, let's move on to letter E. Letter E looks a little bit different. It's got a G there, so that's my hint that this is going to be geometric. But I hope that this setup looks familiar to you. It should look a little bit like our exponential functions, a, b to the x. So much like we did on that last one, in order for me to find the first term, I'm going to find g sub 1, so I'm going to replace my n with a 1. So 1 minus 1 up there in the exponent is a 0, so I have 2 to the 0 power. Guys, anything to the 0 power is always a 1, so this becomes 3 times 1. And 3 times 1 is 3, meaning the first term in my sequence is a 3. That makes sense because remember A was supposed to be our initial amount, and that's what they show there as the initial amount. Let's go on and try the second term of the sequence. So the second term, we write 3 times 2, but this time we're replacing the n with a 2, so 2 minus 1. So starting with that exponent, 2 minus 1 is 1, and 2 to the first power is just a 2. So I end up getting a problem of 3 times 2, which is 6. My next term is a 6. All right, let's try the third term. G sub 3 would be 3 times 2 to the 3 minus 1 power. 3 minus 1 is 2. 2 to the second power is 4. So now I have 3 times 4, which is 12. My third term is a 12. Finally, looking for the fourth term, I'm going to find g sub 4, which is 3 times 2 to the 4 minus 1 power. So 4 minus 1 is 3. 2 to the third power is 2 times 2, that's 4. Times 2 is 8, so I get 3 times 8, 3 times 8, which is an answer of 24. So looking at this sequence, do you see that my pattern is multiplying by 2 each time? And guys, that makes sense because that's what my base is. And that base tells me what I'm doing repeatedly. All right, let's try F and G on your own. So pause the video and give yourself a few minutes to try F and G on your own. So in this case, guys, I see the pattern is 25, 5, 1, and then my next term would be 1/5. And I didn't show the work there, but what I see is I'm dividing by 5 each time, which is where I get that 1/5 as my common multiplier. It also starts at 25, just like I thought it should. All right, finally, let's look at this last one. Back to an A, so that means arithmetic. So it should be following a pattern of multiply or of adding or subtracting. So 12 times 1 plus 4. 12 times 1 is 12, plus 4 is 16. To find the second term, I'm going to take 12 times 2. That's 24, plus 4 gives me an answer of 28. To find the third term, I'm going to take 12 times 3 plus 4. That's 36 plus 4 is 40. And I see that my pattern is adding 12 each time, which is what my slope ended up being. All right, we're going to continue with this objective just a little bit more because sometimes they don't write the rule in this manner that we just saw here. Sometimes they write the rule in this way, and I've actually done this backwards, but that's okay. Sometimes they write the rule in that recursive form that we talked about. So this one's a little bit easier to work with. So this one starts with now. That's where I start. And then it says add 5 each time. So 4 plus 5 is 9. 9 plus 5 is 14. 14 plus 5 is 19, and so on. B, now, again, that's always where I start. But this one's going to be that geometric form because it's multiplication. So this says 4 times the now. So 4 times 3 is 12. 4 times 12 would be 48. And then 48 times 4 would be 192. Finally, C, again, I see multiplication here. So I'm going to know it's a geometric pattern. So I'm going to start at 24, and then I'm going to multiply by a half. So half of 24 is 12, half of 12 is 6, half of 6 is 3, and it just continues on. So again, I think those are a little bit easier to see, but that other form that we talked about is the way that we see why it fits with this exponential because it follows that same pattern. A, B to the X. It talks about where we begin and then what is that constant multiplier, which is our exponential form. All right, guys, I hope that helps in you exploring these sequences. So what I'm going to ask you to do now is I'm going to ask you to use your, or to look at the worksheet that was attached today and ask you to work through that. You're going to be doing the same 3 things. So you're going to first look at a table of patterns or sequences and determine are they arithmetic or geometric. You can write the word out beside it or write just an A or a G. That would be fine too. Then you're going to be asked to write the recursive rule. Remember that has 2 parts, now and next. So for every one of those, both arithmetic and geometric, you're going to write that rule now equals and then next equals. And then you're going to be given some rules and you're going to be asked to find the sequence from that rule. Some of them are going to be given recursively, like what we see on our screen right now. Some of them, though, are going to be given like that last section. Again, that's the harder section, but just take it a piece at a time. Remember, if we want to find the first term, we replace the n with a 1. If we want to find the second term, we replace the n with a 2. And then we simplify what's left. Guys, if I can help you with anything, please reach out. Know that I'm happy to help you and willing to meet with you at 11 o'clock most days. You just need to let me know so that I can be on to do that. We'll talk to you later. Bye.